Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at algebraic proofs. So we're just looking at proving statements using algebra. So we'll start off with an easy one. The product of two even numbers is even. We know that that's true. Let's prove it. So it becomes really easy after you know the trick to this. So the thing is, you can represent any even integer, any even whole number, by writing it as 2 times an integer. So we can represent even integers as like 2m or 2k. And here I'm going to write m and k are elements of z. This is just shorthand mathematical notation for m and k are integers. So that works. Any even number can be written as 2 times an integer. For example, 14 is 2 times 7, 82 is 2 times 41. So these two stand for arbitrary even integers. So what would be the product of those? Well, their product would simply be 2m times 2k, which we know is 4mk. So 4mk would be 4 times an integer. See, if m and k are integers, we know that if you multiply two integers together, it is also an integer. That always works with no exceptions. So 4mk is an integer divisible by 4, therefore it must be even. So what I showed here, what I proved, is that if you have two arbitrary even integers, you multiply them together, you actually get a number divisible by 4, which is always even. We know that numbers divisible by 4, like 4, 8, 12, 16, they have to be even. So we're done. We have performed a series of statements to argue this point, and no one will be able to argue that any of these statements is not true. So now we're going to look at a much harder concept, that of mathematical induction. So mathematical induction follows these steps. You prove a statement for the base case, lowest value of n, assume true for n equals k, and prove that if it's true for n equals k, it's true for n equals k plus 1. What are we doing here? Well, we're going to get statements like this. Sum of first even numbers is equal to n over n plus 1. So the thing is, I want to prove that this works for any integer value of n. It works if n equals 1, if n equals 2, if n equals 3, and so on. But I can't prove all those cases individually. I'd be here, for the rest of my life if I wanted to prove it individually for every single value of n. I couldn't do that. There are infinitely many values. I want to show that this works regardless of whether n is 3 or 3,000. But mathematical induction allows us to get away with this. We don't need to prove every single case. What we're going to do is prove that it's true for n equals 1. That's going to be really simple. Now, what these two statements here are doing is they are allowing us to prove that if it's true for n equals 1, it'll be true for n equals 2. And if it's true for n equals 2, then it must be true for n equals 3. And if it's true for n equals 3, it must be true for n equals 4, and so on. So that is our plan here. So the first step here, proving the statement for the base case, we want for the lowest value of n. So here we're really saying that n is greater than or equal to 1, and also that n is an integer. That's the scope for which we want to prove this statement here. So the base case, all we do is substitute n equals 1. So the sum of the first one even number, the first even number is 2. And if I substitute n equals 1 for here, I get 1 times 2. This is clearly a true statement. We have proved that this statement works when n equals 1. When you have just one even number, it is equal to 1 times 1 plus 2. That's really not shocking. The ingenuity comes in the next couple of steps. So the second step is we're going to assume true for n equals k. So I'm going to assume that if I add up the first k even numbers, 2 plus 4 plus 6 plus 8, now note that the kth even number will actually be 2k. So the reason for that, the first even number is 2, second even number is 4, third even number is 6. You can see that this is always double the number of the even number. So for example, the 32nd even number is 64. So that's why I put a 2k here. So what I'm going to do is I'm going to assume that that will be this formula with k substituted. All I'm doing is substituting n for k here. So we don't need to prove this is true, we are assuming it's true, so we can go to our next step, and the next step is called the inductive step. What we're actually doing is showing that if the previous assumption is true, that if you add up these even numbers you get this, we're showing if that's true, it will be true again if I add one more even number here. So let's do that. So 2 plus 4 plus 6 plus 8, we keep adding until we're 2k, but now we're going to add one more even number, which is 2k plus 2. Now, by the assumption from the previous step, we assume this was k outside of k plus 1. Okay, that was what we assumed and didn't need to prove. So what we have here, so I'll just make that actually look like a plus. So what we have here is that this whole expression must be equal to k outside of k plus 1, and then we've added on an extra 2k plus 2. Okay, so now what we're going to do is we're just going to clean that up. So expanding the first brackets, we get k squared plus k, and then we've got our 2k plus 2. Of course, normal algebra, k plus 2k, I can just simplify as 3k. Now this can easily be factorized. You know how to factorize a quadratic. Two numbers that multiply to 2 and add to 3 are k plus 1 and k plus 2. Now, it probably doesn't look like it, but that's actually proved what I want to. Why is that? Well, what I've shown is that if there are k plus 1 even numbers in this expression, then I can just substitute n for k plus 1. So k plus 1 was n, and then k plus 2 is n plus 1. This formula here still works if n is equal to k plus 1. So, again, the logic of this is we showed that this statement is true when there is one even number being added, one even number. We showed that if there are k even numbers and this formula holds, it will still hold when there are k plus 1 even numbers. So, because it worked when there was one even number, it will work when there are two even numbers. And because it worked when there were two even numbers, then it will work when there are three even numbers, and so on. And so our concluding statement might look something like this. This just says in words what I just said orally. So that's the idea behind mathematical induction. Let's look at another example. So we're going to prove that n cubed minus n is divisible by 3 for all positive integers n. So that means you can substitute n equals 1 and this will be divisible by 3. You can substitute n equals 2, this will be divisible by 3. You can substitute n equals 200, and this will be divisible by 3. Once again, I don't want to go and prove this for every single case, for n equals 1, n equals 2, n equals 3, because that would take infinitely long. So instead, we're going to use mathematical induction. So we want this to work for all positive integers n. So the base case is going to be the smallest positive integer for n, and that's going to be n equals 1. So if we have n equals 1, we get n cubed minus n is 1 cubed minus 1, which is 0. 0 is actually divisible by 3, because 0 divided by 3 is 0, which is a whole number. 0 is divisible by any number. So the base case works. We've shown that this formula is true when you substitute n equals 1. So now what we're going to do is we're going to assume that this will be true when n equals k. So we can assume when n equals k that this will be true. And what we're actually assuming is that k cubed minus k, so I've substituted here n for k cubed minus k is divisible by 3. We're just assuming that is true. Now we're going to show that if it's true for n equals k, if it's true for n equals some number, it will also be true for the next number. So this is our inductive step. We are going to substitute n equals k plus 1 into this formula here. So if we do that, we get n, which is k plus 1 cubed minus n, k plus 1, n cubed minus n. So if we expand that out, hopefully we remember when we expanded these brackets using Pascal's triangle, this is what you get when you expand the first bracket, and expanding the second bracket, you get minus k minus 1. So note that the 1 and the 1 just cancel each other out, and just to make this a little easier to work with, we will go 3k minus k is 2k. Okay, so we have to prove that this here is divisible by 3. So here's the idea. This one here is always going to be divisible by 3 because we're looking at integers. If k is an integer, k squared is an integer, 3k squared is an integer. This will always be divisible by 3. When you divide it by 3, you get k squared, which is an integer. So we don't need to worry too much about this. What we do, however, need to worry about are these two. See, if this is divisible by 3, then these two will need to be divisible by 3. Now, what we know from our assumption is that k cubed minus k is divisible by 3. Note that 2k is equal to negative k plus 3k. So these two expressions here and here, they are equivalent. All that's different is 2k has been written by negative k plus 3k. Now this one here is a multiple of 3, so that is divisible by 3 because of our assumption. These two are going to be divisible by 3 because they're 3 times an integer. So this here is a multiple of 3 plus a multiple of 3. And if you add together any two multiples of 3, like 27 and 9, you always get another multiple of 3. So this here is divisible by 3. So this here just says exactly what I said, why this must be divisible by 3, because each of these things is divisible by 3, and if you add together two multiples of 3, you get another multiple of 3. So we've actually proved it. So what have we proved? We proved that if n equals 1, this is divisible by 3. We proved that if n equals k, if you substitute k and it's divisible by 3, then it will also be divisible by 3 when you substitute k plus 1. So we've shown that because n equals 1 gives something divisible by 3, then n equals 2 will give you something divisible by 3. Substituting n equals 3 will give you something divisible by 3, which means substituting n equals 4 will give you something divisible by 3, and so on for all positive integers for n. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.